Welcome everybody on Zoom. Welcome everybody in the lecture hall. Today, we are going to look into what's inside the black boxes that we had so far, because you might remember that when we looked at object storage or even at key value stores and HDFS, everything was in a black box. We just had sequences of bins, and that's all the data sets were. So now it's time to start looking inside these black boxes and see what we have and what we actually store in the cloud. I will ask you two questions to begin with. I also want to say a few words about the preponderal exam, because I sent an email to everybody, as we do every year, in order to anticipate on the number of people. So this is only for mobility students, exchange students. This year we have a problem, is that the number is so high that we are not able to organize this physically. I'm still talking with the examinations office to see if there's any way or any solution we can find. And I will keep you posted on that, right? So if we find something. All right. Let's go ahead and ask you two questions. The first one is on the CAP theorem. You might remember CAP. I told you you cannot have the three of them. It is not possible for a system to be atomically consistent and available and partition tolerant. You have to make a decision and remove one. So in the case of DynamoDB, do you remember which two of the three actually hold? The majority is indeed correct. It is consistency. How do we know that? Well, remember the vector clocks and the possibility that you have two conflicting versions in different parts of the network. This is actually what happened in the example that I showed you. So this is why we don't have consistency. However, we have partition tolerance. In fact, we had an example of network partition in the course. And we have availability because it remained available even with the network partition. So consistency is drops. What about HDFS? I don't have a question for this, but can anybody tell me what HDFS is? Yes, go ahead. Maybe yes, say it in the microphone. That's correct. It's correct what you're saying. Go ahead.
Yeah, just to say to people on Zoom, I said consistency and availability because it's not tolerant to partitions that may happen sometime.
Exactly, this is correct. So indeed, HDFS is not partition tolerant, simply because if you have a network partition, then all the sites that doesn't have a name node cannot continue to work. Now you could argue, yes, but we have standby name nodes and observer name nodes that could take over. Imagine the huge mess that is going to be if there's a network partition and then you have a name node on one side, a name node on the other side, and then the network reconnects again. This is absolutely not part of the HDFS protocol to deal with that. So this is why, indeed, you are correct. It's not partition tolerant, but it is consistent and available, as long as there is no partition, basically the definition. Okay. Do I have another question, I think? This is my second question. Sorry. If you want, in the case of HDFS, to create a directory, that's the first question. And the second question, to get the actual data, I mean the blocks, for a file, with which servers do you communicate? Is it only the name node, only the data node, or is it the data node for the directory, the name node for the actual data, or the name nodes for the directory and the data node for the actual data? Wow, we have a majority and a very clear majority. You can still change your mind if you want, but be careful, the majority is not always correct. But in that case, it is the name node for creating the directory and the data nodes to get the actual blocks for the file. All right, very good. So now I'm switching back to the slides. Wonderful. Okay. So a recap. I love to start with a recap because then we just bring back to our memory what we've been doing so far. It's always good to repeat things every couple of weeks. So we've seen data shapes, that there are tables, trees, graphs, cubes, and text. And we're actually going to look at a lot of these data shapes in that course. The only one that we don't really cover is text, but we'll look at pretty much any other data shape in here. Today, we are going one more level in the stack because we've completed level 1. It's like a video game. We are done with storage. We know how to store data as a cloud in a cloud service, meaning it's a service managed by a company like Amazon or Azure or Google and so on. That is a worldwide service where you just upload your data, download the data. We've also looked at other kinds of systems that are not hosted in the cloud, but that you install on your own premises, so your own machines, which is HDFS, right? So the difference between HDFS and S3 and the others is that HDFS, you need to manage it. You need to pay somebody and an administrator in order to take care of the cluster. Of course, you still have the possibility in most of the providers. In Azure, it's called HD Insights. Amazon, there's Amazon EMR. So you can click on a button and a cluster of HDFS machines are going to magically pop up out of nowhere. That's the magic of the cloud today. But these are just machines just for you. It's not anything that you are sharing as a service with other people. So everything on the file system is yours. Okay, but now it's time to move on to the next level. So we look into syntax, of course, not every syntax because we are going to do it step by step, but basically syntax can be a lot of things. Syntax often means that the data that is sitting in the black boxes on the cloud storage is actually text. It's textual, it's characters. So you all know, you're computer scientists, you know how to map characters to bits, right? There is the old ASCII encoding, even though these days it's more UTF-8 using Unicode. But basically it's text. And you can actually encode a lot of different data shapes in text. For example, it can be text. CSV would be for tables, XML and JSON for trees, RDF over XML for graphs. We'll look at it later. Turtle also for graphs, XBRL for cubes. So all of that we'll keep for later because graphs and cubes, they are so special that I'm keeping them for later. But XML and JSON are going to keep us busy. But here's the motivation. Imagine it's CSV. Who knows CSV? You all do, right? Who knows CSV? Right, comma-separated values. Even business people know CSV. You can open that in Excel, you can download it, and so on. All right. So CSV is just syntax for a table, right? You can actually, when you just look at the top here, if you ignore the part at the bottom, if you look at the top, who sees a table just looking at the text? Right, many of you. And that's the thing, it's a syntax for tables. I'll ask the same question about XML and JSON later. We'll see. My goal is to give you the intuition. But basically here it's straightforward, right? It's syntax for a table. Be careful because as simple as it looks when you actually do it that way, it becomes very quickly complicated when you try to handle all the corner cases. Because what happens if you have a comma that is actually part of a value? Then you need to escape it with quotes, right? But what if you have quotes in the value? Then you need to escape the quotes. So you see, it's never ending. So CSV has a lot of parameter tuning. You can actually change and not use a comma, but instead use a tab or use a different character, use a space, a semicolon. You can use also a different way to escape the quotes. In that case, for example, what we have is that we escape the quotes with double quotes. So the first quote here, let me show it. The first quote right here is the actual start of the string, and this is the end of the string. So you see, this is the value. This here, this double quote, is a way of saying this is an actual quote character that is part of the value, right? So it's quote, incompleteness, another quote, again, there's two just to escape it, and then theorem. This is how when you parse CSV and you see a double quote, you know that it's not the end of the string, you know that it's just an escapes quote. It's like a backslash in JSON. All right. So you see, there is an RFC, request for comments. That's where a lot of the standards are. In practice, I'm sorry to put it that way. In practice, it's a huge mess because there are so many ways of doing it. And every time, so you will open a CSV file, you need to try to fine tune and select all the parameters and so on. But anyway, it's widely used and it handles tables. We looked into the, yes, is there a question?
Is there a special case for the empty string that we can use two quotes to represent the empty string?
I think what I've seen so far in CSV is for an empty string, you just have a double comma. So you have a comma and immediately another comma, and then you know that there's nothing. I think you could also imagine to put two quotes and that's an empty string, but I think that the common practice is to just have the two commas that follow each other. Okay, right.
Thank you.
But you know that's the right thinking. You need to think of all the all the cases. In fact, it's part. I can even tell that to you because that's part of the experience. Maybe some of you will have when you design things. When you try to design a new thing, can be a new syntax, a new query language, a new system, and so on. At first, things will look simple. You know, how complicated can it be, right? You just do this and do that, and then you have an intuitive thing. But this is just a prototype. And very quickly, what you'll notice is the corner cases start arriving, and then it transforms into a more complicated engineering problem. And some of it can even take years to build with plenty of people. So you should never underestimate the engineering effort that it takes to go from a simple hacked prototype to an actual complete documented working system. This is really a lot of work to actually make it work. All right. So having said that, another thing is the normal form. We saw that the first normal form means we cannot nest data. We looked into other normal forms. So here is Boyce code. There are so many of them. There's the second, the third Boyce code. There's even a fourth, a fifth, a sixth, and so on. These are basically intuitively, very, very intuitively, a normal form is the opposite of a join, right? When you bring the tables in a higher normal form, you split the tables into meaningful units in order to avoid data duplication, problems with insertion, with deletion, with updates. So basically, in normal form, you would have several tables, and denormalizing the data means that you join it back into a bigger table. But the idea and the whole reason why I'm actually repeating normal forms is that this is in that course, in our course now, what's happening to normal forms. So of course, it feels strange to be telling that to you after you spent an entire semester in your bachelor's knowing the normal forms. But this is in the very specific context of big data. I am not saying normal forms are bad. Normal forms are really good in the context of a relational database with a lot of rights, you know, in a system, for example, behind an online store and so on. In the context of big data analytics, we throw the normal forms away. And in order to throw them away, you have to first know what they are, right? It's very important. Okay, so now we can have data that is highly normalized. And this is for the case that it is write intensive. So these are the good old relational databases. You know, even DynamoDB would be write intensive and so on, even though it's not a relational database. But it's highly normalized, and we avoid update anomalies this way because we write a lot, right? Now, in big data analytics, this is where we are. It is read intensive. We don't really touch the data or modify the data, but we read it in immense quantities. In this case, we denormalize the data because we want to be read efficient. It's so much easier to read a single table or a single collection than to have to join collection. Joining in big data analytics is extremely costly. This is why we want to avoid the join, and avoiding the join means denormalizing. we pre-compute the join is another way of putting it by denormalizing. For whom is that clear? Okay, so you see this inverse relationship between joins and denormalization, right? That's very, very important. Okay. Now, if I give you a concrete example, that would be a normalized data set with 3 tables. We have the sales here, we have the customers, and here we have the, I think it's, oh, I'm hiding it with my head, the products. And you see that this links here, this is a foreign key pointing to that primary key. So here we reference the product, here we reference the customer. So what happens if we denormalize that? Well, to denormalize, we join it back to a single table, and here you go. And of course, you can realize that there's a lot of duplication in there. You see this number appears 3 times, and so on. So this is the cost of denormalizing, is that it's eating more space, but we don't have to join anything anymore. We can just read it in a big data setting. Is there a question?
Does the customer table make sense if there's no data but the name?
Oh, yeah, that's because it's oversimplified. Of course, in reality, you will have the name, the address, the city, the country, and so on and so on. Right? You're absolutely correct. Maybe even I should add it so that it's fully clear. It's because I oversimplified. Let's put it that way. Okay. All right. So we denormalize, and this is a denormalized. It's not denormalized all the way to below the first normal form because it's still a table. It's still in first normal form, but it is not in the second or third or Boyce code normal forms. We view this as a collection of tuples. Remember that row, tuple, record, these are all synonyms. It's all the same thing. So a table is a collection of tuples. Now, what is a tuple? Well, a tuple, mathematically, it's an ordered sequence of values that are taken from sets, right? So a tuple is when you talk about Cartesian products. But as I told you, the way we look at tuples in big data is more as a map, because we map the attributes to a value in every tuple. This is a map, right? We map this to this. So if I write it again now mathematically, product is phone, price is 800, customer is John, and quantity is 1. That would be normally this, the first line. Yes, my eyes are not good enough. So that's the first line right here. This is the tuple if you view it as a map from strings to values, right? Now, you can also write it that way, right? You can express it differently with some text, because this is not really text. I mean, yes, if you use Unicode symbols, you can still make it work, in LaTeX and so on. But if you really want a simple text format, then this is what it would look like. This is exactly the same thing. This is a map. This is a row of my table. But here I'm not using CSV as I could have done before. I could have said phone, 800, John, 1. Here instead, I'm explicitly giving you the map by also mentioning the attributes that are maps to the values. This is one row, one tuple, one record of the table. Who recognizes the syntax? I'm sure you all do. Oh, wow, this is awesome. So say it all at the same time. Okay, that doesn't work. Who can tell me? JSON, yes, exactly. This is JSON, and we are going to study it. So you see now, let's do it for every row. This is now a representation of the same table, but as a collection of what we will see are called JSON objects, right? So this is the motivation for why we are looking at that syntax. We are looking at the JSON syntax because we can already use it as an alternative to CSV in order to represent this table right here. Of course, you might object, yes, but there's a lot of inefficiency. We're repeating the fields and so on and so on. Yes, but we'll get benefits out of that. Okay. And the benefit is coming right up. Nestedness, because I said we denormalize. Sorry, my voice. This is what happens when you talk a lot. So nestedness means that you can have tables in tables. Can you do it in CSV? Who thinks we can? Who thinks we can't? We have a majority for can't. Well, you can't do it in CSV, but of course, you always need to say things with a pinch of salt, because if you take a hammer and hit it enough, you can still come up with a way, right? But it's going to be complex, right? Natively, CSV does not allow you to nest. However, with JSON, we can actually nests like this. And I'll tell you everything about the syntax and so on. But basically, we have a way in JSON to express that sort of nested table here as an array of objects, right? Do we have a question on Zoom?
Yeah, there's one question. Does the JSON syntax fix the CSV problems with the double quotes and separating character?
Yes, I would argue that it does, and the standard is more respected than CSV. Even though, well, I'll come back to that, to the details. But in essence, yes, absolutely. I'll cover how to escape quotes and so on shortly. All right. Okay. So what's going to happen now that we saw that JSON is able to nest and handle denormalized data in that way is that we are moving from homogeneous collections of flat items. It's only a fancy way of calling a table, really. It's a homogeneous connection of flat items. Every row is flat. We are moving over now to heterogeneous collection of arborescent items. So now if you speak French or Italian or Spanish, you will get what that means, right? This just means tree-like arborescence, right? We'll see that these are actually trees. Who sees trees here? Who doesn't see trees here? Not yet. You'll see them in 2 weeks. In 2 weeks, when you look at that, you'll see trees. This is what I will make you see. All right, but we're moving from homogeneous collection of flat items to heterogeneous collections of arborescent items. This is denormalized data. This is normalized data. All right. There is another name for heterogeneous collections of arborescent items. We also like to call them semi-structured data. That was a hype back then, right? Now today it's the blockchain, you know, but there was a hype on semi-structured data maybe 10 or 15 years ago. That was the big thing. Semi-structured data is kind of in the middle between text and fully structured tables, right? So this is what we'll cover in this lecture and in 2 weeks for the modeling and validation part of semi-structured data. What's important is that it is standardized. We have XML, which we'll cover, which is a W3C standard. W3C, who knows W3C? It's the same people who standardize the web, HTTP, HTML, and so on. So it's a consortium who has plenty of working groups of people who meet every week for 2 hours over the phone. And probably they might be using Zoom now. I would be curious, actually. But back then, we were using the phone. And they come up with standards, right? ECMA is another body of standardization, which covers now JSON. Recently, it took it over. JSON used to be an RFC, and now it's ECMA. ECMA is the same as ECMAScript, which is just JavaScript, really, right? A standardization of JavaScript. Okay. All right. So what is really syntax in the sense that we'll cover it as text? Well, it's really a yes-no question. It's really a yes-no question. And in fact, if you remember your Theoretische Informatik courses, you might remember the notion of language, right? Context-free grammars and automata and so on, right? A language is just a subset of the set of strings, right? You can view it that way. And when you have a language, you can ask the question, does that string belong or not to that language? It's yes or no. So in that sense, XML and JSON, or syntax in that sense, is also a yes-no question. And there is a fancy name for this yes or this no. We call it well-formed. If the answer is yes, meaning if a text document is in the language XML, we say it's well-formed XML. If it is in the language JSON, we say it's well-formed JSON. And otherwise, it's not well-formed JSON, or it's not well-formed XML. What we will not say, and that's a word of caution because this is a mistake that a lot of people make, we are not using the word valid here. Valid means something else that we'll cover in 2 weeks. We are really using the word well-formed. Okay. This is an example of XML, and I'll cover the details of it. This is an example of JSON, what it can look like, and we'll cover both. Who sees trees here? Who still doesn't see trees? Okay, you will, I really promise. You will. Okay. It's like the Borg, you know, in Star Trek. You will be assimilated. Resistance is futile. All right. JSON string. I'm going to present JSON building block by building block. Sorry. We are going to start with strings. There's actually 6 building blocks in JSON. This is the first one. A string in JSON is always double quoted. You cannot single quote it. That doesn't exist. So it's double quoted, and inside it's characters. Now, and that's the question that you asked earlier, how do we deal with special characters, or even what happens if you have quotes and so on? Well, unlike CSV, in JSON, there is only one way of dealing with quotes inside a string. It's backslash quotes, right? You use a backslash. That shouldn't really surprise you. I mean, escaping characters with backslash, I'm pretty sure all of you saw it somewhere, be it in a programming language like Java or C++, on the shell and so on. So that's something very natural to a computer scientist. And so JSON uses backslashes to escape. The same goes with the new line, which is \n. And with special characters, you can use \u to have a 4-digit code for the Unicode number of the character that you want to use, right? This is in base 16, by the way, between 0 and F. Okay. So let me put it that way. You can use fancy characters and so on. Typically, it's going to work. What will not really work, or you might start having issues with, is control characters and so on, right? But typically, when you have data, these are not really the sort of things that that will happen. It's mostly going to be text. All right. Next, we have numbers. Numbers is not more precise than that in JSON. It's just an optional sign followed by digits, followed by an optional decimal period, followed by digits, followed by a capital, or a lowercase or uppercase E, followed by a plus or a minus, and then by digits again, right? So this is basically what it looks like. So a lot of that is optional. So this is an example with, so this is pi, right? So 3.14115, 15 is a number. Here you have another example. And what that means is, I'm sure it's obvious to most of you, but just making sure, this means minus 1.2352345 multiplied by 10 to the power of 5. This is called the scientific notation. There are also calculators that would display numbers like that, right? So this means that plus 5, you're basically shifting the period by 5. So that would actually be the number 123,450, right? Okay, so this is a number. The decimal period is optional. The leading minus is optional. The exponent is also optional. If you don't say, then it's E0. And E plus 5, you can also have E minus 5 if it's a negative and so on. But it's pretty simple, right? In fact, that's the reputation of JSON. JSON is super simple, and that's probably the reason why many people actually love JSON. What's very important here is that we do not have at that level the notion of types of numbers, double, float, integer, decimal. We don't have any of that here. It's just text, and this is just text that expresses a number. Note that there is no quotes. There are no quotes in there, unlike strings. So this is how you distinguish strings from numbers. Next, we have Booleans. This is very easy. It's true and false, unquoted, just like that in JSON. Okay. I don't really think I have much more to say in here, right? It's just true and false. And here also super easy, null, which represents the fact that you don't have or don't know or don't tell a value. For some people, it represents the absence of a value, but there is a subtlety here. You could have completely absent or a null, which technically it's not exactly the same thing. But basically null, it's similar. You can think of it like the Java null, the C++ null, like what you see in many languages, okay? These 4 are special. They are called atomic. This would actually be values you could have in the first normal form in a table, right? So these are atomics. In addition to these 4 atomics, we have structured types. This is what you would not allow in a table in the first normal form as a value. This here is an array. You notice the square bracket right here and right here. That also shouldn't surprise you. In plenty of imperative programming languages like Java, C++, you actually use exactly the same syntax. even JavaScript, and comma separated. Right. What you can have in an array is any kind of value in JSON. Can be a string, can be a number, can be a Boolean, can be a null, can be an array, or can be an object. We haven't looked at them yet, but it can be anything. What is very important is that you can mix. You see here, we have the 5 of them. This probably is something you wouldn't be used to seeing in a Java program. Why? Because in a Java program, you typically would have a shared type, right? You would have like everything is a string, so you have an array of strings or a vector if you use the libraries and so on. But the type should be the same. All right. But here, what is new is that it doesn't have to be the same type. It can really be a list of pretty much anything completely mixed. This is what we call heterogeneous, right? And finally, the 6th one, this is an object. Again, shouldn't surprise you. It's using curly braces. There are also languages that like this sort of syntax for objects. And this is just the key value model that we've already seen so many times. It's a map. Actually, the first time I showed you a JSON object like that was in the context of maps. It's a map from strings to values. The strings here, we call them keys, even though you might also find people who call them properties or fields, you know, so there are many ways that you can call them. So key, field, property, don't be surprised, right? This all means what you have here. It must be quoted. And then you can have on the right, the values, anything, a number, a Boolean, a string, an object, a null, and so on. All right? This is an object. So you see 1, 2, 3, 4, 5, 6. And that's it. That's JSON. It's just that. Okay. Now let's dive a bit more. I told you the word is well-formedness, right? So the first documents that you see, that's text, but it is not well-formed JSON. This is why I put this red cross on the right, right? Why is it not well-formed JSON?
The keys are not quoted?
Exactly, the keys are not quoted. You need quotes around the keys. You could have quote square bracket 1 square bracket quote, that would be a valid key. Then it's a string, right? It cannot be an array, it cannot be an integer, and they must be quoted. Here is another example. Why is that not well-formed JSON? Yes?
The same key is repeated twice.
Exactly, the same key is repeated twice. This is not a map. You see here, this is twice the same key. So this is not a map. And indeed, it is not well-formed JSON. Now I put a little something at the bottom of that slide. Probably see it, should. The reason is, it's not a must, it's a should. If you look at the original RFC of JSON, it says you should not have twice the same key in a JSON object. So technically, it's not forbidden. But I'm sure that many of you are probably big fans of treating warnings as errors, right? So if you see a should, you should treat it as a must. If you create JSON, it's basically in order to be interoperable. If you do create documents like that, it will not be parsable by many JSON libraries that enforce that there cannot be duplicates. So for that course, for our course here, we do not allow duplicate keys here. And that's why we say it's a map technically, all right? This is an example of data set. Actually, we will see it probably in the exercises. It's the Great Language Game data set with, I think it has 16 million objects like that with a target language. And then you have an audio sample that is played and then a multiple choice question. Was it Chinese, German, Italian, or English? The player guessed that it was German. It was in fact Italian. There's the date and the country where it was played. And we have 60 million of them. This is one of the data sets that we can actually play with. But you see, this is an example of actual data that is using JSON. Is it in the first normal form? No, why? Yes, microphone is right there. This doesn't seem to work today. You heard that it distorts the voice. Go ahead.
Yeah, it's because of the array of choices. Because
yes, exactly. So this would be a row of a table, right? This could be a row. But you see that the third column would then be something that is not atomic. This is not atomic. So this breaks the first normal form. But it's fine because this is semi-structured data. So in semi-structured data, we can absolutely have that. Okay. So now if we come back, you probably now understand this better. I mean, I'm sure a lot of you already saw JSON before, but many of you didn't, right? And that way now you know JSON. So my question to you, just making sure, does everybody see that this right here is a syntactic representation of this table right there? Who sees that? Awesome, right? So this is the idea. Every JSON object is one row of the table. But we saw now that we can also represent tables in tables, and the way we put tables in tables is with arrays of objects. This is an array of objects right here. So we have product phone, orders, which is an array of objects. Order, you see it's an array of objects. What are the objects in the arrays? These are the rows of the nested table, right? So this is why we have an array of objects. This is a very common pattern that you will see in denormalized data sets that use JSON, all right? So you see there is a bit of structure here, but it can also be heterogeneous. Okay. Are there any questions on JSON before we move over to XML? No questions. Who finds JSON easy? Okay, that's great. That's the reason why it's so popular. Now, I want to say two more things before we move on. First, there exists parsers or libraries in JSON that do not enforce that keys must be quoted. So if you have an unquoted key, it will still accept it and parse it correctly and add the quotes automatically. Typically, they only do that for simple keys, if there is no space, if there is no special characters and so on. So this is why you might find on the internet JSON documents where the keys are not quoted. The rule here in general, this is actually general in computer science. If you write something, you should strictly enforce all the rules. So if you create JSON, always quote your keys, always. If you read JSON or write a parser, it's fine to be a bit lenient, then you make yourself more compatible with other files, right? This whole thing about do you throw an error, do you accept, do you fix, and so on, actually has been a very long ongoing debate in the W3C in the context of HTML. In the context of HTML, for example, if you have an HTML file page, you probably know that if you have errors in the HTML page, it's still working. For example, you can actually drop the slash body and the slash HTML in the end to gain some space, and it will still work. So in the HTML community, there is this idea of being lenient to errors. XML and JSON is the opposite. In XML and JSON, you want to enforce the rules. And again, it's really not about, it looks like, you know, they are raining on the party by wanting to enforce these rules, right? But in computer science, you are really doing yourself and everybody else a favor if you produce documents that follow the rules, because this is interoperable between different technologies. All right? Okay. So let's move on. I have a bit of time, I think, before the break. Let's move on to XML. XML is scary. Who is scared now that we are going into XML? Some of you are scared. I totally understand. XML is a bit more complex. It's more complicated. It's also older than JSON. But the point is, it's in wide use in the industry. Many companies use XML. So now you're going to ask me, why are they using XML and not JSON? Well, of course, they are also using JSON. But the thing is, XML is not just the XML syntax. It's a whole ecosystem of standards and products that work and that are enterprise ready. This is the reason why it's such in wide use. So it's important to also know XML and to know what it looks like and understand it. My goal is that in the end, you will see them as trees and automatically parse them. There are plenty of examples of use of XML. I can give you a few examples. For example, in Switzerland now, the banks can issue electronic statements that can directly be submitted to the tax office with QR codes on the PDF. This is an embedded XML file. So they did pick XML for that technology. Another example is that in some countries, it started in Japan and in the US, but now many more countries are following. The financial reports that public companies have to file every quarter, right, with the balance sheet, income statement, the cash flow statement, and so on. It used to be some boring PDF file, right? It's a printing on printed paper, or a PDF, which is a more modern version. But the thing is, a computer cannot read a PDF. So this is why 20 years ago, there was an effort by the accounting community to try to make it machine readable. And guess what syntax they use? Yes, XML. So it's called XBRL, the technology. And actually, you have huge quantities of data in XBRL formats that a lot of people want to analyze for all the public companies that are filing their data in that format. So it's in the US, in Japan, now it's even in the European Union since very recently. And in Switzerland, it's also, there was a consultation by the Federal Council, I think, for sustainability reports, where XBRL is also on the radar. So you see, XML exists, it's in use, and you will probably see it in your career. But don't worry, because I'm not going to teach you everything about XML. I'm just going to stick to the very basic of what you should know, right? Because otherwise, there could be a whole semester course on all the intricacies of XML. I'm not going to do that to you. I'm just going to teach you the very basics. Let's go, let's take a break. I think you deserve a break after I throw XML at you. So let's meet at 3:15, and then I will introduce you to XML.